Right then. Whoa, how did that just happen? Well, you're about to find out. Okay, hi everyone, and welcome back to Cloud9 TV. It has been a while, several months, since I posted my last video, E equals MC squared explained. Since I've uploaded it, it's become my most popular video to date. So thank you so much for that, and I'm now going to kind of continue that theme of and style of video forward with a short mini-series I'm starting right here, right now. So when I talk about forces, most of us will think of things like pushing, pulling, maybe gravity. Some of us will start thinking about people like Isaac Newton, Galileo, but we're only really scratching the surface here. So in the next 4 videos, I'm going to talk about each of the 4 true fundamental forces of nature. Gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each video covering a different force. So today we're starting with perhaps the most well-known of those 4 forces, but also the most different. Once again, gravity. It's a remarkable thing, gravity keeps us on our feet, allows us to do everything we do. Without it, we'd be pretty stuck. But how many of us actually know what it really is? Now, gravity is a force that has been on our minds since the time of the ancient Greeks. Since the time of people like Democritus, who first thought up the idea of atoms, and Aristotle, who said that every object had its natural place in Earth. For example, a balloon, its natural position is to rise up to the heavens. But it was Ptolemy who started to really think about the way gravity worked. He published a book that was kind of an amalgamation of years of astronomy and mathematics and science that was able to predict the position of planets in the sky for many years to come. And it wasn't for another 1,000 years until someone called Nicholas Copernicus took on Ptolemy's ideas and began to experiment with them and devise a new system at which the sun was the centre of the solar system and the Earth and other planets orbited around it. These ideas were adopted by Dutchman Johann Kepler, who took them further and was able to develop a fully fledged theory of how the planets revolved around the sun. Now this is all well and good, and by now we have developed a good theory of how our planets orbit the sun. But what about on a more local scale? What about, for example, here on Earth? Well, it turns out, my friend, that was the very next step to be taken by a man called Galileo Galilei in Italy. And he devised a series of experiments to work out how objects fell on Earth. And to his surprise, and the surprise of most other scientists of the time, when you drop an object, it doesn't fall with a constant velocity like most people thought, but it actually accelerates towards the Earth. Through his experiments, Galileo was able to accurately obtain a value for this acceleration under gravity on Earth. 9.8 meters per second squared. And what that means is every meter the water bottle moves, its velocity is increased by 9.8 meters per second. But that was just the start, because the next step was taken by a man in England who went by the name of Isaac Newton, because what Newton did next no other scientist had done before him. He took the ideas of Kepler, Copernicus, Galileo and Ptolemy and mixed them all into one universal law of gravitation. He came up with an equation describing the force of gravity between 2 objects at any position in the universe. F equals g m1 m2 over r squared. And what that's saying is the force of gravity at any point between 2 objects is equal to Newton's gravitational constant multiplied by the mass of one object and the mass of the other divided by the distance between them squared. With this equation, scientists were able to predict the orbits of planets with greater precision than ever before. In fact, Newton's theory was so good in that it lined up exactly with what astronomers had seen for thousands of years. This theory had cemented Newton's position as one of the greatest scientists of all time. And with this equation and others he formulated, many people believed that everything had been discovered, that the universe was complete. But Newton wasn't so sure, because he could see some issues with his theories. For example, what is space? And what is time, for that matter? And it's all well and good that objects can attract each other at great distances. How do they do it? What carries the force? And that wasn't all. You know, I said earlier how Newton's theories were able to accurately predict the orbits of the planets in the sky. Well, all except one. In fact, the orbit of Mercury was out by 0.43 seconds per year. A tiny amount, yes, but easily predictable by astronomers of the time. This was just another hint that our view of the universe wasn't quite complete. Now, as hard as he tried, Newton simply couldn't find an answer for this problem, and so it was left for future generations of scientists to discover. Of all the scientists who were able to help amend Newton's theory of gravity, 3 were more important than any other. One was an Englishman called Michael Faraday, who had experimented with magnets and how they interacted with each other. And from this he developed a theory of magnetic fields with force lines along which the force acts. Now don't worry if you don't understand this, because I'm going to be talking about this more in later videos. But the whole idea is that he and a Scotsman called James Clerk Maxwell, who came along and put it all into mathematical formulae, were able to devise this idea of a force field. a field in which the force between two objects is carried. In their case, this was a magnetic field, but this surely could easily be applied to the theory of gravity, a gravitational field. But it took one man to tie it all together, to finish what Newton, before him, Copernicus, Ptolemy and Democritus had started. It took a 25-year-old physics graduate from Germany, who worked at the patent office in Bern, Switzerland, to tie all the loose ends together and come up with the best theory of gravity we have to date. And his name was Albert Einstein. Einstein first published his theory of relativity in 1905, in which he explained that space and time were not two separate things as we previously thought, were actually both different aspects of four-dimensional space-time. In this theory he talked about moving objects and the velocity of light. But his greatest work, the work that tied everything together, came 10 years later, in 1915, and it was called his theory of general relativity. In this theory, Einstein described gravity not as a force, but as the effect of warping of an otherwise perfectly flat space-time caused by mass and energy. In other words, mass and energy warps and curves space-time, much like by putting a bowling ball on a stretched rubber sheet. The sheet is warped. Objects were attracted to each other due to the way they warped space-time, the gravitational field. He summed all this up using Riemann's equations of curved space into one beautifully simple equation. RAB minus half RGAB equals 8 pi GTAB, where RAB and half RGAB represent the curvature of space-time, and TAB stands for the energy of matter. Here G is the same constant that we talked about earlier, Newton's gravitational constant. With this equation, Einstein had summed up the last 2,000 years of scientists and Greek philosophers' work on gravity. But this equation wasn't quite complete. Einstein wasn't happy because this equation predicted that the universe should be expanding, and so he added in a cosmological constant to correct this. But in fact, this constant has a very interesting story, and it does not end here. And today we actually use this constant when talking about things like dark energy. So that is the story of how gravity has developed through time, through its foundings in the work of Ptolemy, to reaching its pinnacle 100 years ago in Einstein's theory of general relativity. Many people at first didn't agree with relativity, and it took many years of confirming predictions before people began to understand it. For example, as I've already mentioned, his theory of relativity predicts the curving of space-time, not just space, which means that time should be distorted in a gravitational field too. It was understood that time slowed down deeper in a gravitational field, so that here on Earth time should run slower than it should up in the orbit of the moon, for example. Many people didn't understand or believe this, and in fact when they sent up the first GPS satellites up into space, they didn't account for this time dilation in their equations, and because of this, each day the GPS was out by 10 kilometers. These were massive effects, and the scientists working on GPS had to correct this quickly. Another effect of general relativity is it doesn't really have any boundaries. It predicted, for example, that say in the collapse of a supermassive star, the centre of that star will collapse in on itself so much that it will create a hole from which not even light can escape, a black hole. Again, at the time people couldn't understand this and refused to believe it, but by now we have observed hundreds of black holes, and in particular we know of one, with a mass 1,000,000 times that of our Sun, the centre of our galaxy, the Milky Way. Another prediction that came out of general relativity was that space-time, just like for example a sea, could be rippled through fast energetic movements. For example, two black holes orbiting each other. Again, this prediction is hard to believe, but in late 2015, 100 years after Einstein first predicted it, gravitational waves were detected by sensors in America and Europe. And lastly, remember earlier when I was talking about pesky little Mercury? Yeah, well, Einstein fixed that too. His theories weren't just good, they were excellent. And there you go, that is gravity. General relativity is our most up-to-date and precise theory of gravity at the moment. But this might not be the case for long, as all that is set to change as we try to combine two different areas of physics: general relativity and quantum mechanics, which I'll talk about more in later videos. But who knows, maybe in 50 years time we'll be talking about a new theory of gravity. A theory that unites general relativity with quantum mechanics and all other aspects of science into one theory of everything. Okay, so I do hope you enjoyed this video here. This is, as I say, the first part of a 4-part series that I haven't filmed the other parts for yet, so any advice you've got, anything you want to tell me about this video, put in the comments down below so I can take that on board. So if you did enjoy that video here, you can, as normal, do 4 things. You can like the video, you can comment down below with suggestions for future videos and anything you've got to say. You can share the video to spread the love, and if you haven't already, you can subscribe to my channel by clicking the red box down below, and you can also turn on notifications by clicking the bell next to it. But until next time, see ya!